Hello everyone, myself Muhammad Waris Sanan. In this video, I'm going to discuss the proof of Thevenin's theorem. Okay, so before going to the proof of Thevenin's theorem, I'll first discuss a summary of Thevenin's theorem. So let us start the video and prove the Thevenin's theorem. So first of all, let us understand what is Thevenin's theorem is. So a Thevenin's theorem is a theorem which is widely used in circuit analysis, and this theorem is a very important theorem. Let us now understand this theorem by considering a network, very complex network consisting of large number of independent sources, voltage and current sources and resistances. So we will consider the DC circuits only, okay, for our simplicity. And suppose this is a network N and we need to find a response across this branch. We call this branch, the resistance of this branch, as load resistance. Okay, let us now name the terminal. These are the terminals, AB terminal, and we need to find response, say for example current. We need to find the current through this resistance RL, which is load resistance. So Thevenin's theorem states that we can replace this network, which is a very complex network, by a voltage source VTH in series with a resistance RTH, where VTH is the open circuit voltage across the terminal AB and RTH is the equivalent resistance looking into the network from the terminal AB by putting all the independent sources to 0. So what is VTH? VTH is, we have this network N, and if we open circuit this terminal AB, and if we calculate this voltage, open circuit voltage, this will be equal to the VTH. And now about the RTH, Thevenin's theorem says that to find RTH, this network which contains independent sources, voltage and current sources, we put all the independent sources to 0. All independent sources are put to 0. Okay, and now looking into the network from the given terminal, we find the equivalent resistance, and that will be equal to the RTH. So this is what the Thevenin's theorem is. We need to prove this Thevenin's theorem in this video. We are going to prove this theorem. Means why we can say that this network is equivalent to the given network. Okay, so in order to prove Thevenin's theorem, what we do, we have this network N consisting of independent sources and resistances. What we do, we connect a known current source, external current source I, and then calculate this voltage V, and if this network N is replaced by a voltage source, we are calling it VTH, in series with a resistance RTH, and again we do the same thing here also. We will calculate the current and voltage relationship in this network. Now, if the voltage and current relationship in these two networks, let us consider this is 1 and this is 2, are identical, then we say that these two networks are also identical. Means that we have proved the Thevenin's theorem. Okay, so let us start. In order to find out the relation between voltage and current in this network, in the first circuit, we will use the concept of superposition. Okay, in this network N, we have multiple independent sources. So for the sake of simplicity, let us consider two independent sources. One is voltage source Vs, another is current source Is, for the simplicity purpose only. Okay, we can have multiple voltage and current sources in this network, and we have lot of resistances. So we are not bothering about the resistance, just take two independent sources which are connected to the network N. Okay, so these are internal sources, and this I which we have connected across the terminal AB is an external source. Okay, so by using the concept of superposition, we can find this voltage V as the algebraic sum of individual contributions of all the sources Vs, Is and I. Now let us consider the contribution for the external source I will be as A naught I, and for the other sources Vs and Is as A1 Vs and A2 I. Okay, so here you can see we have the contribution from the external source, and this is the contribution from the external source. Now let us write these two, internal and external contribution, in a different manner. V can be written as A naught I, and let us call this internal contribution, replace this internal contribution by a term B naught, where B naught is A1 Vs plus A2 I. Now our job is to find the voltage and current relationship in second circuit, so that if the voltage and current relationship in the second network is coming out to be similar to this equation, so we say, or identical to this equation, we say these two circuits 1 and 2 are identical, which will prove the Thevenin's theorem. Okay, so now starting with this equation, let us call it equation number 1. Whenever we call this equation, we will call it by equation 1. Okay, so if I ask you, or if we need to calculate the value of the constants A naught and B naught in this equation, how we can calculate that? So case number 1, we are going to find the value of A naught, say for example. So if we put the value of B naught equals to 0, we will get the value of A naught as V by I. Okay, let us now analyze this condition. What is the meaning of saying B naught equal to 0? We have this B naught as A1 Vs plus A2 I. Now if we are putting this B naught to 0, what we are actually doing, we cannot put this A1 and A2 to 0 because these are some constant values, and this Vs and Is, sorry, it is Is, Vs and Is are two independent sources. So in order to put this B naught to 0, we are just making Vs to 0 and Is to 0. So let us write this, we are putting independent sources to 0. Independent sources to 0. We are putting independent sources to 0. Now when we put the independent sources to 0, we are getting A naught as the ratio of voltage and current, which is the ratio of voltage and current is the equivalent resistance, because V by I is R. We can understand this by analyzing this circuit. Suppose we have a resistance box and we need to find the equivalent resistance or the total resistance in this box. So there are two different ways to find out the resistance of this box. One way is to connect a current source, known current source, known value I, and then find out the voltage and then find out the potential drop across the terminal. So R equivalent will be equal to V by I, because in this resistance box there is no any independent source or there is no any source. So the passive network here contains only resistances, and the equivalent resistance can be found out through this method. Another way is to connect a voltage source. We can do the same thing by connecting a voltage source. This is the resistance box and this is the terminal, AB terminal of the resistance box, and if we connect a voltage source across this terminal, known voltage source, and calculate the current going inside the network, so the resistance R equivalent will be equal to V by I. So these are the two ways we can calculate the equivalent resistance. Whatever be the resistance of this box, we can calculate through this method. So in this way also, in this network also, we can see that when we put B0 to 0, what is happening? This network is now reduced to a passive network because all the independent sources are now put to 0. So this is a passive network now, means it contains only resistances in this case. Now this current I is an external source. We know this value of this current I and we calculate the ratio V by I to get the value of A0. So this is actually giving the equivalent resistance of the network. Now come to this circuit 2. What is RTH? RTH is the, now see, this is the concept we have just discussed, how to calculate RTH. We are putting all the independent sources to 0, and if the independent sources are put to 0, then the equivalent resistance looking into the network from the terminal AB will give you the equivalent resistance RTH, or Thevenin's equivalent resistance RTH. So this is what happening here. The same thing is happening here. We are now putting all the independent sources to 0 and we are calculating the ratio V by I, which is R equivalent, and this will be equal to the RTH. How? Now let us do the same thing in this network also, in the second circuit also. So if we put this internal voltage source, we have only one voltage source in this network, which is VTH. If we put this voltage source to 0, so putting voltage source to 0 means we need to short circuit the path. So we are just short circuiting this path. So now you can see this current will flow through this path like this, and the resistance offered by the network will only be equal to RTH, or we can say the ratio V by I will be equal to RTH. So V by I in this case will be equal to RTH. So you can understand the similarity between these two equations, V by I RTH and V by I is A0. In this case we are putting all the independent sources to 0. In this case also we are doing the same thing, putting the independent source to 0, and we are getting the value RTH. Okay, so there is a similarity, not similarity, but these are two identical. So we say A0 is actually equal to RTH. The A0 which we are calculating in circuit 1 is equal to the RTH of the circuit 2. Okay, now let us analyze the second case now. In the second case, what we are going to do, we need to find the value of B0. So we have this equation A0 into I plus B0. So in order to find B naught, what we can do, if A naught is not A naught, sorry, we put I equal to 0, not A naught, because A naught is a constant quantity. If I is equal to 0, we can say B naught is equal to the V. Now what happens if we put I equals to 0? Let us analyze this. This is the network N, okay, and we have connected a current source across this terminal, current source I, and this is the voltage across the terminal V, and these are the terminals A, B. Now if we put this current source to 0, that what we are doing here, I equals to 0, so what happens? Current source putting to 0 means we are open circuiting this terminal. So we are actually we are not doing anything with this network, we are just making this current source open circuit so that current will be 0, and we are getting this voltage across this terminal V, which is equal to B naught. So we say that this V is actually the open circuit voltage, VOC, across the terminal. When we have opened the circuit, opened this terminal, so VOC is the open circuit voltage across the terminal AB, and we are not doing anything with the network. This complex network has all the independent sources and resistance connected, okay. We are just doing one thing, that we are putting external source to 0. So the voltage that we are getting here is equal to the constant B naught, or B naught is equal to the V, which is the open circuit voltage. Now if we analyze this Thevenin's voltage, what is this Thevenin's voltage? VTH. It is the open circuit voltage across the terminal AB. So whatever the load you have across the terminal AB, we just need to remove this load and we need to find the voltage across the terminal AB, which will be the open circuit voltage. And here also we are getting the same thing, open circuit voltage, which is equal to V naught. So if we find the voltage, open circuit voltage from this network, from circuit number 2, we have circuit number 2 like this. Let us draw the circuit here also. This is the Thevenin's equivalent voltage source and Thevenin's equivalent resistance, and this is what we have, current source here, I, and the voltage across the terminal V, okay. Now if we put this current to 0 in this case, the voltage that we are getting here, suppose if we are putting this to 0, means we are open circuiting this, we are just removing it and we are putting it to 0, it will be VTH, it will be equal to VTH. So here the open circuit voltage that we are getting is VTH, and here the open circuit voltage we are getting here, it is equal to B naught. So we say that these two networks are identical, because by removing the current source in both the cases, here we are getting B naught and here we are getting VTH. So we say B naught, which is equal to open circuit voltage, is actually equal to VTH. So we say that the equation voltage current relationship in this case, in circuit number 2, this is circuit number 2, is V is equal to RTH into I plus VTH. Now you can see these two equations are identical, because A naught is the resistance and B naught is the open circuit voltage, and here RTH is the equivalent resistance and VTH is the open circuit voltage for the same network. So we can say that these two equations are identical. So the networks must be identical. So in this manner, we have proved the Thevenin's theorem that if we have a network N consisting of large number of independent sources and resistances, we can replace this network by a voltage source VTH in series with a resistance RTH. Okay, so this is all for today's video. Thanks for watching.